I want to talk today about a topic that is actually in chapter 12. It is section 12.2 in your textbook. So we're going to do a very brief overview. It works better in this unit than it does in the stuff that we'll do in chapter 12. So if you are struggling with anything, you'll want to go to section 12.2 in chapter 12, not in chapter 3. Okay? So we have talked a lot about linear data. And we know that a scatter plot, a line of best fit, only works when we have a linear model that we are modeling here. However, often a straight line pattern is not the best model for depicting the relationship between these two variables. We talked about a curved graph, and this problem is really indicated by a distinct curved pattern in our scatter plot. We don't like curved patterns, so we are going to force the data to be linear. This is called linearizing data. We're going to make it linear. It's not linear, so we are going to use logarithms and square roots. I hope you know, and I'm going to assume you know what a square root is. A logarithm is not something we're really going to cover in depth in this class. However, it's a mathematical tool that you can use in pre-calculus and calculus and things like that. For now, as long as you know where the log button on your calculator is, you don't really need to know what a logarithm is. And I'll put a link in the Edpuzzle video. It should pop up right now in a note that you can watch if you look at this information to learn a little bit more about what a logarithm is. Again, we don't necessarily need to understand mathematically what's happening. We just need to know where's the button on our calculator. Okay? So I'll give you a second here. There's only 5 data points. Go ahead and make the scatter plot for the original data. I don't know about you guys, but this to me looks very exponential. This does not look like a line. We can even see the data growing exponentially. So this will be part A. I've drawn my scatter plot. Part B asks us, would you apply a transformation? And if you would apply a transformation, the data needs to not be linear. So yes, we will want to apply a transformation to this data because the data is not linear. And the data looks approximately like a power function or maybe an exponential of some sort. Or it could be like 2 to the whatever it is. But it does not look very linear to me. It's growing exponentially in some way. All right, so part C is going to ask us which one. We're going to figure out which one here in just a second. And to judge the best model, we are going to look at the R values. We are going to look at the scatter plot. And we're going to look at residual plots. All right, so a residual plot, let's, in part D here, it's saying calculate the linear regression for the original and the transformed. So let's go ahead and look at just the original data. Of course, we haven't transformed it yet, so we're just going to look at the original data as given to us. Okay. And go ahead and actually type this data into your calculator because we are going to want to get the equation for the least squares regression line and the R value as well. All right, so hopefully you've had a chance to put your data in and run it in your calculator. So I have my data here on my linear regression. Let's go ahead and write the least squares regression line. We are predicting the population of, I don't know what this is, but we're predicting the population. It doesn't give us the context of the exact population. But we know we're predicting some sort of population. And my data is not going to work for year 0 outside. It's extrapolation, so I've got a weird intercept. Use year as my x variable there. Okay. All right, so there's that. Let's put our R value in there. Our R was 0.98. However, since this is not linear, the R value is essentially useless to us. A really, really, really strong R value. However, my data is not linear. Okay? And we can look at this by looking at our residual plot. Okay? So in part E, we're going to draw the residual plot. I know I'm kind of skipping around for a second here, but we'll transform it once we kind of have our original data entered in here. Okay? So let's draw our residual plot. And in our residual plot, we are looking for the most scatter plot, like the most random residual plot that we could have. We want to see no pattern in our residual plot. And if we have truly no pattern in the residual plot, that is telling me that it is a good model. Okay, so I'm going to go ahead and draw my residuals in here. So the easiest way to do this on our calculator is I have my data already in list 1 and list 2. Your calculator will calculate the predicted values for you. Okay, so I'm going to go up here and create a rule for list 3. I'm going to type in my equation to list 3. And instead of putting our variable, I want to take all of the years, which I currently have stored in list 1. So I'm going to put list 1 in there, and it will calculate out for all of the corresponding values in list 1 what we would predict this to be. Okay, now remember that your residual is your actual minus your predicted. So I'm going to throw my residuals over here into list 4, and that would be the actual minus the predicted, which is list 2 minus list 3. The actual values minus what my equation has predicted them to be. So over there in list 4, those are my residuals. You are welcome to graph this on a scatter plot on your calculator. With this little of values, I think it's easier just to go back over to your graph and let's graph them here. We're going to keep our same x-axis for a residual plot. I have a residual of 8. It's going to be somewhere up here. Okay, so a residual of 8, a residual of negative 3.5. Whoops, not that one right there. A residual of negative 8, a residual of negative 5.5, and a residual of 9. If I am looking at this data right here, this is looking like it shows a pattern to me. This looks like a quadratic in my residual plot. That is bad, okay? Pattern equals bad. So since this one has a pattern, that's telling me that this is a bad model here, a bad fit, okay? So let's go back to our original question. The original goal was to transform my data and find a new equation. Your best bet, so this is the answers for the original, this is for our transformed. You kind of want to do the opposite of what the graph looks like. The opposite of an exponential is a logarithm. So I am going to take the natural log of both sides and just see what happens. Okay, the natural log. So I'm going to take the natural log of all of these and the natural log of all of these. Now the easiest way to do that in your calculator is I want to keep my list 1 and my list 2, but my list 3, that was the ones I typed in from my least squares regression line here, so I'm going to just write over list 3. And what I'm going to do is I'm going to create a rule for list 3, and I want list 3 to take the natural log, this button that's down here underneath log, LN, find the LN button on your calculator. I want to take the natural log of everything in list 1. And then I'm going to pop over here and I'm going to take the natural log of everything in list 2. And I'm going to graph my new list 3 and list 4. I'm going to put this onto a scatter plot. You can just watch my graph just to show scatter plot list 3, list 4. What our new graph looks like, we can compare it to, let me turn my box plot off, excuse me. That looks a lot more linear than I had originally. So originally we could see a true curve. Well, would you look at that? They make a nice straight line now. Pretty wild. Okay, so when we transform our data, we took the natural log of both sides. Now I still want my calculator to find my least squares regression line of my transformed data. Okay, so I'm going to go calculate my linear regression with my new lists, because now I've put my data into list 3 and list 4. And here's my new equation. Look at this R value, you guys. That's insane. It's a crazy R value. When we write our equation, we are no longer predicting the population. We are predicting the natural log of the population. It's super weird. I know. We're taking a natural log of a population. I mean, what? We'll take it back at the end, okay? But the natural log of the population. And now we can use our same values here. 441.888, I guess, plus 58.84 times, again, the natural log of the year. All right, let's make our residual plot. So I'll do that again on my calculator so you can see it. Always good to get the practice here. I'll go into my lists. I will make list 5 my predicted values for my new one, my natural log of my population. So I have negative 441.88 plus 58.84 times the natural log of year, which was list 3. Okay, there's my predictions. Here are my actual values. Okay, in list 6, I'm going to take actual minus predicted. List 4 minus list 5. What? Oh, I need to write it up here. Okay, list 4 minus list 5. There it goes. Create your rule when you're up here. There's my residuals. So I'm going to, again, plot these values here. Okay, so we did this. Oh, let's put our R value was 0.99, something crazy, basically 1. Okay. And then here I'll make my residual plot for part E. And all of mine are actually really close to that line. So, I mean, it's basically just going to be 5 dots up here. I'm not going to put a scale. This is a much more random pattern. Okay, this is more random. So for this guy here, random equals good. Whereas this one I could see a definitive U. This one now I've got in a completely random pattern. And the random pattern means that that is a good fit for the model. Okay, so here we go. We've transformed our data. We've linearized it. We can find an R value. We'll talk more about kind of the purpose of this. There are 3 more examples that we'll do in class to kind of get a better feel for it. For now, let's answer our last question, part F, and I'm running out of space. Actually, I can put it up here. Let me go ahead and do that. I'll put part F up here since I answered my other question on a different sheet of paper. So now we need to predict the population in 1993 from both the linearized and the back transformed equation. So let's go ahead and calculate that. Go ahead and throw it in this equation first, and I'll give you a second to do that. To plug in 1993 to this equation here. All right, I have my answer for the original. When we plug it into our transformed equation, we're just going to plug it in right here, just like you did before. However, before you can plug in the year, you do need to take the natural log of the year. Okay, so here we would take, again, our natural log button. It's right here on my calculator of 1993. And that is the value that we will plug in over here to multiply by this guy. So I guess I'll just do it here. I'm going to do 58.84, and then I'm going to add a negative 441.88. Okay, so our transform data, this guy is the predicted natural log of our population. We want to take this so we can actually find a population, because the natural log of the population, I'm sorry, that's pretty meaningless to me. I don't really care about that. To undo a natural log, you use your exponential. Okay, and if you don't remember a lot about natural logs, it's okay. You're going to take e to this power to undo your natural log. You should have an E button on your calculator. Mine is in blue above my natural log. So I'm going to do e to this 5.15 value. And now I have my prediction for the population. You'll notice that these two values are close. However, this one will be a better approximation.